Good evening. Today we are going to discuss one of the theorem in quantum mechanics known as Ehrenfest theorem. In the scenario of lockdown because of new coronavirus 19, I just came across this software in the mobile and just trying to get used to it. So there will be some glitches during this recording. I would like to say sorry for that. Please excuse me for that. Let us start the class. Here we'll discuss the step-by-step calculation of the theorem. There may be some method where you can do a shortcut, or you can do in other way around in a short calculation way, but we are trying to understand this one, and I'll try to explain you each step, and you will do with me. That will help you try to understand why we are taking some terms here and there. I'll explain all the things. So before entering the Ehrenfest theorem, we have to understand what is expectation value in quantum mechanics. We do talk about expectation value where you see the terms like delta. Suppose this expected average value of x, where x is defined as the position, where you write like integration psi star x operator, then psi, then across the volume you'll write d tau. Okay, so we do like these things. So first of all, we have to understand why we put this operator in between these two wave functions. There can be a case where you could have put the x like this, no? Suppose integration, you could have write x operator. It can be any operator, by the way. Psi star psi, then d tau, or you could have write psi star psi, then x operator, then d tau. Okay, but we choose to put this operator in between these two wave functions. The reason is, if you go by this method, suppose x cape psi star psi, and here what you can do, then you can integrate. You just consider psi star psi as the second function and x as the first function. If you go in that way, since generally in expectation value we put the limit as minus infinity to plus infinity, so if you do as x as the first function and psi star psi as the second function, then you will reach a point in the calculation where you get things like this. For example, I'm just giving you the momentum operator. Suppose you have minus infinity to plus infinity. You want this p operator psi star psi d tau. Okay, you have p operator, then psi star psi d tau, or you can write suppose x for one dimension. Now if you do this integration, then I can put the value of p operator, which I know, which is the minus infinity to plus infinity. I put the limit here, minus I h cross, suppose one dimension, so I will write d dx. Then you will have a psi star psi, then the integration, which is suppose dx. Okay, suppose dx. Wait a minute, as I told you that I'm just new to this software, so there will be some glitches while doing that. Okay, so in that case if you do, what happens, you have the thing like ddx, let the minus is cross outside, integration, then you have psi star psi tx, and you have the integration here. Integration, again differentiation, that means those gets cancelled out. The limit was minus to plus infinity. Ultimately you will have like this, psi star psi minus to plus infinity. Now we know that for a wave function to be physically acceptable, when x tends to infinity or minus infinity, your wave functions must have a finite value, which is 0, which is because 0 is also finite value. So that means you will get a result of 0. Similarly, you might get expectation value sometimes 0. That's possible, because the expectation value of momentum sometimes can become 0. Suppose the particle is moving both in the plus x and minus x direction, moving in both direction equally or harmonically, then you might get the momentum expectation value as 0. That's the point. But here, without using any value of psi, without any putting any function value, we are just getting from the whatever value you use of psi, you will get a 0 expectation value. That should not be correct, I think. And the other way around, you could have go like this as well for expectation value, which is psi star psi. Suppose you put the p operator here at dx. Okay, but this is mathematically not mathematically acceptable, because then you will be writing in place of p operator, you would be writing minus ih cross ddx, and there is no function that side to operate with this ddx. It's a meaningless. That means the earlier one will not give you the correct, means will give you the 0 result whatever the wave function will be. Second one is not mathematically acceptable. So the only option that remains is minus to plus infinity psi star p cap or any of dynamical variable corresponding operator psi tx if it is one dimension. This is the only thing which will be left out for us to calculate the expectation value, and that's why we calculate by this way. Now we'll enter the Ehrenfest theorem. So in Ehrenfest theorem, what exactly we are going to talk about? I have used just my I already did the calculations in my copy, so I just using their photo 1 by 1 pages, sometimes the half of pages, and I'll try to explain each sentence or each steps of the calculation. Okay, let us first understand the theorem. What is written? It says that the theorem states that the average motion of a wave packet agrees with the motion of the corresponding classical particle. For example, dr dt, or you can write dx dt for one dimensional. Dx dt is equal to momentum divided by mass. Okay, momentum divided by mass is nothing but mv. Since the whole Schrodinger equation is for non-relativistic particle, here we don't talk about relativistic motion, so I can easily write in place of momentum as mv. So mv divided by m, you will be left with velocity v. Okay, and dx dt again gives you the velocity. So that means if you time differentiate the position, you will get the velocity. This is okay. This is okay if you go by the classical theory or you go by Newtonian mechanics. That dx dt of something is equal to, obviously if x is the position, it will be velocity, no problem. But in quantum mechanics, there is a problem. The problem is because you don't know about x. Means in Newtonian mechanics or in the equation of motion, whatever we have learned earlier in mechanics, which is followed by us, the macro bodies. Suppose for example s is equal to ut plus half at square. If I provide you initial velocity and the acceleration, then you can tell me the displacement at any given time. Similarly for v is equal to u plus at. If I can provide you initial velocity and the time, you can tell me the final velocity at any instant. Okay, those things are possible because we know if we know the present, we can predict the future. Okay, or if we know the future, we can backtrack to the past or the present. We can come back to the past. Okay, but here the problem is we don't know the present. So it's very difficult to guess the future because the present is already in probability. We'll talk about the probability of everything. So the present is in probability, then how can you guess the future? That's why the Ehrenfest theorem becomes critical, because it somehow creates that link between classical and the quantum wave. But the only thing you have to be concerned here, that the wave packet which we are talking about in quantum, which is not very vast, it's very small wave packet, or the width of the wave packet is considerably small, because then only we can make this average equals P by M. For example, what we'll do here, we'll try to prove that T, expectation value of position by time, is equals to expectation value of momentum by m, mass. Now I cannot do dx dt here directly, I have already told you why. So that's why I will be doing ddt of expectation value of position. Now the expectation value of position, or average value of position, will give me the average value of x for a given wave function psi and psi star throughout a large number of calculations. Okay, I'll bring the average value. So and the differentiation of that will give me the P by expectation value of P by M. Okay, similarly the second one is dp dt will be the minus del V. dp dt means you can say the Newton's second law, force, rate of change of momentum, and we know that force is equals to minus the grade of V. V is the potential energy, potential. So this is also possible in classical, but we'll show it that here in Ehrenfest consideration this is also possible. Okay, so we'll first tackle the dr or dx dt in one dimension equal to P by M. Okay, so first of all what we'll do, we'll write the expectation value of position. That means you write what is this x for a given wave function psi star and psi. So you'll just simply write, you don't need to put the limits here, it's known. So psi star x psi, suppose dx, you can write d tau as well, no problem. Okay, no issue. So you can write dx, suppose psi star x psi dx, expectation value of position. Then you will take the time derivative. In the next step you can put like that, you can take the time derivative, which is done here, ddt, this ddt part. Okay, so ddt of x. So in the right hand side you will write the time derivative. Now here you have psi star x and psi, three functions. All three can be the can be a function of time. Okay, position, psi star, psi, all three. But the thing is that in quantum, when I am talking about the probability, I already told you I cannot calculate dx dt, because dx is the Newtonian mechanics, is means the velocity. But here I cannot guess the future because I don't know the present. That means the dx dt here, it simply will be 0. If I could have calculated dx dt, then I could have easily write dx dt is equal to P by M, which is not the Ehrenfest theorem. But I am calculating the expectation value, then I'll take the derivative, then I'll get the momentum by M, which is the Ehrenfest theorem. So that's why I will dx dt, which is 0 here in our in this consideration in quantum mechanics, because this is not possible to calculate. Okay, so that's why you can see here in the next step we've written psi star x, means first we are deriving by time to psi. Since psi is a function of both time and position, that's why I am using the partial differentiation sign here. Del psi del t, d tau, plus again I will do this time psi star. So del psi star del t, again the x psi will remain out, and del x del t is 0. So that's why the differentiation of x by time is not required. Okay, now leave it there. That will be equation number 3. Then first I will write the time dependent Schrodinger equation, which is we know IH cross del psi del t is equal to minus h cross square by twice m del 2 psi plus v psi, which, well, you know these things. Okay, we have reached the Ehrenfest theorem by doing all those things. So what I'll do, I'll take the IH cross on the right hand side here, and this del psi del t on the left hand side, and that will be our equation number 4. And in the next step I will write the complex conjugate of equation number 4, That means psi can be complex. So we will write psi is complex as psi star, which you all know already. So del psi star del t, and since you have I, that can become minus, all those things. The reason is that we'll put this del psi del t and del psi star del t values in equation number 3 here. This del psi del t, del psi star del t. We'll put those value in equation 3. Okay, come to next page. Now in equation number 3, you can see we have put the values of del psi by del t and del psi star del t in equation 3, and we have substituted the value, this one and this one. In the next step, I'll take the 1 by h cross common. So if I am taking this as common, then the first term there is no problem because minus is inside, I have written, but here there was a minus, na? I have taken the plus as the common, so the minus will be there. This minus will multiply with this, it become plus, and this becomes minus. Okay, then in the next step, what we'll do, we'll bring out this h cross square by twice m, which is here and here as well. So we'll take the common outside here. Okay, because this v term will get cancelled out. Since potential means psi star x v psi and v psi star x psi are same thing, because potential's operator is potential itself. Okay, x operator is x itself. So that means psi star x v psi and v psi star x psi, these are same thing. But if in place of v there is p operator, if it would have been p operator, then you cannot make both the things equal, because p operator has a differential operator inside. Okay, so this thing can be done, both are equal, opposite in sign, you cancel out. Then you bring out the h cross by twice m outside as a common. I is already there waiting, and h cross is there, so h cross square will come out, one h cross cancel out, you will have this h cross by twice im. Inside you will have psi star x del to psi and minus del to psi star x psi. Okay, now in the next step we'll see what we'll do. Now what we'll do, let us take this term del to psi star x psi. It's integration now outside, this part different, this part differently, this part differently, in between them we have minus sign. So let us integrate one by one. Let us do del to psi star x psi integration. What we'll get, let us see. So I've written del to psi star x psi d tau. So here you will consider del to psi as the first function and x psi as the second function, like integration of u v dx. Suppose both u and v are function of x. So you will do step by step integration. Suppose this is u, this is v. So you will do this. You'll get first this, the second order differentiation will become first order differentiation. Then you will put the limits which you already know, minus to plus infinity. Then you have this. Okay, now again you can see x psi del psi star. Again, if x tends to infinity or minus or plus infinity, psi tends to 0. So x is infinity, psi is 0. Infinity is 0 multiplied is in fact a 0 thing. So this will vanish. The first term will vanish. Okay, because we know when x tends to infinity or minus infinity, psi has to be a finite quantity, so it tends to 0. So 0 multiplied by anything, even infinity, it becomes a 0, the power of 0, which was discovered by Aryabhatta, isn't it? Okay. So it becomes, this term becomes 0. So we have this is equals to, we remain by this. Again we will integrate this part. This time again this is u, suppose this is v. Okay. We got this one, no? Del to psi, del psi star, del x psi. Okay, we'll keep it there, and now we'll go and integrate. Yeah. So this written here, yeah. We'll integrate this again. again u, this part, first part is u, second part is v. So again you will use the same logic and you will be left out with this psi star del 2 xi d tau. Okay, do it yourself, you will get this thing. Now this is done here. So using equation 9, equation 6 can be written as, so what was equation 6? We will check. Equation 6, this was equation 6, ddt dx psi star x del 2 psi d tau plus h cross by twice m del 2 psi star xi d tau. In the next page we got the value for del 2 psi star xi d tau, means we got the value of del 2 psi star xi, this one. And similarly, if we get the value of this one, we can calculate this one as well. If you got the value of this one, you put the value here. The first term is this psi star x del 2 psi. So equation 6, yeah, first term is same, we are not changing this one, sorry. And the second term, let us check. Second term is psi star del 2 xi, which has come from here. Okay, we put here. Then minus h cross by twice im, you have psi star x del 2 psi, you bring this inside the common, psi star common, h cross by twice im is common, take outside, you put this, you get this thing. Now we'll try to solve this. Okay, so here you can see we have written x del 2 psi minus del 2 xi, this inside part. Okay, so I have written, take it, x del 2 psi is equal to x del 2 psi minus, I can write x del 2 psi and I can write del 2 xi as del dot del xi. I can write like this, del dot del xi, because del dot del is equal to del 2. Okay, so you can write like that. So if you can write del dot del xi, then I can further go. What I'll do, I'll keep this del dot outside and I'll take this del inside. Now del is like ddx in one dimension, isn't it? So this will once differentiate x and again it will differentiate psi, two functions. That's what you have done here. You have del dot psi del x. So first you write suppose psi del x operate, then plus, again x will remain and you will write del psi. Okay, sorry I couldn't write well here. Okay, as the mobile screen is too small, so somehow I'm trying. Maybe in future classes it becomes a little more, I'll become a little more comfortable in doing this. Okay, for a time being you have to go like that. So you got this. Then again the first term is same. Then you will take this del dot inside. So first this del dot, you have del dot psi del x. First term is like this, no? So you will have, first it will work like this, del psi dot del x, then plus the psi will remain outside, this del enter here, it become del 2 x, del 2x. So you got two terms. Similarly, when this del dot work on x del psi here in the second term, you get two terms, which is del x dot del psi plus x del 2 psi. Okay. Okay. So here now you can see del x dot del psi and del psi dot del x, same thing, both are plus, we'll get twice of del psi dot del x, dot product, same thing. Okay, next term you have psi del 2x and x del 2 psi, but this x del 2 psi will get cancelled out with this x del 2 psi, the outside x del 2 psi, and this will cancel out. What remain? Psi del 2x, minus sign outside, you will have minus psi del 2x. Now del 2 means what? In one dimension it's like this, na? d2 dx2. So you are doing d2 dx2 of x. What you'll get? You get 0, because first you will do ddx of x is 1, then you will do ddx of 1 is 0. That's why the second term will vanish, and you are left with minus 2 del psi del x. The del x means again what? Del means ddx of x, which is 1, gone. So you are left with 2 del psi, or in one dimension I can write 2 del psi by del x, this term. Okay, now I'll put this term, this value here. Question 10, it was like this, no? So we just calculated this term, so we'll put the value of this here in equation number 10. So once you put the value here, what you get, this h cross I by im is already there in equation number 10. You can see this part is already there, psi star is there. That means like minus h cross by twice im is already there, isn't it? And you are putting the value of psi star is already there, and you are putting what? Minus 2 del psi del x. So you are putting minus 2 del psi del x, and you have ddx. Okay, so this 2 will come out, this 2 and this 2 will gone, minus minus will become plus, finally you will get this thing. Inside, if I just rearrange the things, so inside I will get 1 by m, this step, where h cross by I, or you can write minus I h cross del psi del x, which is equivalent to momentum operator. That means what we are getting? We are getting d dt of x is equal to 1 by m integration psi star minus I h cross del x psi d tau, which is the expectation value of momentum. So I can write this. So the first part is proved. Okay, the first part is done. Now we'll do the same kind of calculation for the second part. Now what we'll do, now the second part was dp dt is equal to minus grade of potential, isn't it? So first we'll write the expectation value of momentum, then we'll take the differentiation. Okay, you'll take the time differentiation, and like the earlier case, similarly you do step by step. Okay, then you'll get the, ultimately if you do step by step, it's there in my pages, you can see. If you try by yourself, or you can ask me in the comment section if you don't understand any of the steps, then if you go step by step, then ultimately we'll get this thing. You can show here this, you can see this step, ddt of px is equal to minus integration psi star del v del x psi d tau. Since potentials operator is a potential itself, but here you are getting the del v del x, that means del v del x. If you are trying to calculate this, its operator will be del v del x itself. So that's what you are getting here. Okay, so which is equivalent to the expectation value of del v del x. The minus is outside, so you can put here. So which is again equal to rate of change of momentum is equal to minus of grade of potential, which is the case in our classical physics as well, or the mechanics which you know already, you have studied in the mechanics, which is you have learned in high secondary or in the first sem or second sem. First sem I think the same thing. Okay, so hence both the things, that rate of change of position is given by, not exactly position actually, the rate of change of expectation value of position is equal to the expectation value of momentum by mass, and the rate of change of expectation value of momentum is equal to minus of expectation value of grade v, where v is the potential. And this was the Ehrenfest theorem. That it looks a lot of steps, but if you practice if you practice very hard, and I think you should practice these equations, then you will be able to complete it within 5 to 6 minutes. And if you can do that, it will give you a lot of extra time in your examination, because if it comes in examination, it will come around for 5 marks or 6 marks. So if you can complete 5-6 marks in 5 minutes in examination, then those 60 marks paper, if you are completing 5 marks question in 5 minutes, that means you are giving yourself a lot of extra time to tackle some critical questions which do come and which should come in examination, about 10-15 marks. So you are providing yourself an extra time to tackle those questions. So this was the Ehrenfest theorem. So we discussed, let us go to the beginning. We discussed about the expectation value, why we put always the operator between psi star and psi, why we don't put the operator in one of the sides. Now you understood that. We discussed already that. Then we discussed the Ehrenfest theorem and some step-by-step calculation for the first part. And as I explained you the first part, I assume that you can complete the second part by yourself, and you can take the help of my steps here, my calculation steps. You can go by that, and I hope you can calculate that. It's not that difficult. So thank you very much. Put your comments under the comment section and I will again say that since I am using this software for the first time and I am just using this in my mobile, so the screen space is very small, I couldn't write the long equations, so that definitely brings some kind of difficulty for you, but I hope in the future I can rectify these things and will come with some better solution. So thank you for today.